Okay, my name is Eric Hayden. I'm a meteorologist with the Weather Service in Morehead City, North Carolina. Appreciate you joining us this morning. This is our advanced SKYWARN for 2020. If you have any questions, you can email me. You'll have my email address once I send you a certificate. And I usually tell folks it could take up to a week depending on what we have going on in the office. This presentation is already on our website as both the recording and the PDF. So if you have internet trouble, if we have any issues on our end, you can always hop over to that and scroll through both the PDF and the recording. So if we have any technical issues, don't worry, you won't miss out. You will hear me, and you should be hearing me now just fine, and you'll see the presentation over your computer screen. We'll send a course certificate as soon as we can, probably over the next week. If you made a mistake in your email, let's say you don't get the certificate, you're wondering where it is, make sure you signed up with the appropriate email, because I know some prior classes we had some spelling mistakes in the email, and that's why they didn't go through. This is our advanced class. We go way more in depth. You should have already taken a basic class, and that's where we lay down the groundwork of what to report to our office. That's what we're most concerned with. This advanced class is giving back to you the science, so we go way more in depth on the science. If you haven't taken the basic class, it's okay, but please, as a follow-up, go through one of our basic SKYWARNs so you have a better foundation for reporting severe weather to us. We're going to briefly cover it in this class, but the main part of this is more science-oriented. This is one of many SKYWARN classes we have. We have 4 basic ones throughout the year. The 2 main ones are Basic SKYWARN, which is springtime, thunderstorms, hail, and high winds, and basic winter. Those are our 2 main classes we teach all the time. And then the other ones are flood and tropical or advanced. So as many as 5 depending on the year. Those come less frequently, but we do scatter those in to kind of make you a year-round spotter so that you're used to all the different types of weather we get. We always put this information on our website, weather.gov/Newport, and we post it to social media as well. Our main goal is, yes, we're going to teach you some things, but we really want you to report bad weather to us when you have bad weather where you live. As a way to keep you informed, we do put all this training on our YouTube channel. If you go to our website, and again, you're going to get these links, so don't feel that you need to jot them all down. We have a current schedule section, when to report, how to report, and then lastly, YouTube training. We have all of our training up on YouTube via the website, or you can, of course, always go to NWS Morehead City and search that on your YouTube device. So again, our goal is to make you a year-round spotter. A little housekeeping with the class itself. Throughout the class, if you have a question, ask it through the webinar. I won't get to them until the end, but I don't want you to forget it. So if something comes up that you're not clear about, ask the question. Then at the end, I'll go over all the questions I get. If you have a mobile device that has a microphone, any phone, iPad, iPhone, Android has a microphone on it, you can ask a question via the mic, or if you're on a personal computer or laptop like I am now, most of yours that have a camera built in also have a microphone as well. You can ask a question that way. Just raise your hand, I'll call on you, and then I'll unmute your line. Right now, all of the mics are muted, so you don't have to worry about background noise. All right, so that's housekeeping and what the class is. Some of the things we're going to go over today, radar principles. First, we're going to talk about what to report really briefly. Again, this top part is much more thorough in the basic class, but this class is going to get more into the science. We're going to talk about Dual-Pol radar, something called CAPE. What does that mean? Precipitable water, supercells, squall lines, and bow echoes. I know we went into them a little bit with the basic class. This will be much more in depth. As far as the Weather Service is concerned, we're from Eastern North Carolina, so we cover the eastern quarter of North Carolina, but notice all of the offices in the country. We have over 100 offices to serve you. To speak to that point, when we talk about 800 numbers and ways to report, you're going to want to hook up with your local office to find how they want you to report. And I'll explain that here in just a minute. Here's our local office. We cover, again, the eastern quarter of North Carolina, so the Outer Banks, the Crystal Coast. If you live here locally, as far inland as Kinston, Snow Hill, Greenville, over toward Williamston. And this yellow area goes out 20 miles into the ocean, covers the Albemarle, Pamlico Sounds, and the local rivers. So we do forecasts and warnings for that entire yellow area. This blue shaded area is beyond 20 miles. We do warnings out toward the Gulf Stream, but the forecast itself is done by the Ocean Prediction Center, which is part of the National Weather Service. If you live down toward Wilmington or Raleigh or up toward Northeast North Carolina, it's not that you don't have a local office. You're covered by either Raleigh, Wilmington, or the Wakefield or Richmond office. So we cover this part of the state, and our sister offices cover the rest of the state. We are open 24 hours a day. This is a picture of us during Florence. Again, we're here staffed for bad weather. Our building is designed to withstand storms. It's a brick building with hurricane shutters on it. So we stay here when the weather is bad. We're a high location. We increase staffing depending on the weather. We may only have a few of us during a quiet day, but then a tremendous amount of us are at the forecast office when we have something like Florence. The next couple slides will go over our website. If you just remember weather.gov, click on your part of the country, that will bring you to your local office. If you live in Raleigh or up toward Maine or New York State, just click on the state you live in, and then you can get down to your local office. For us, it's weather.gov/Newport. For any of the sites, if you click on the map or enter your city or zip code, you can get a specialized forecast. And it shows you how warm or cold is it going to be, chances for precipitation and wind. And it comes in a text format for the next 7 days, and then also an icon-based forecast to show you what we're expecting. If you want a little bit more meat to the forecast, you can scroll down the page and get an hourly forecast, a marine forecast, fire weather, aviation. So there's a lot of details on that website. You just go as in-depth as you want. So that's a little bit about who the Weather Service is. Now where SKYWARN comes in, it's a volunteer program run by the National Weather Service. And the goal is to give us ground truth reports. And what we mean by that is this tree damage in Warsaw, if that happens to your location, call it in. Let us know what is actually happening. Give us that ground truth of what's going on with our weather. I do want to point out that these spotter reports really help us with our warning decision process. You help us gauge how strong a storm is. It adds credibility to a warning. Let's say that you confirm a tornado or confirm large hail. We will update the warning with that information. So the warning continues, but we'll insert that a trained spotter has reported this, and that adds credibility to the warning to verify that, hey, not only is the warning out, but it is actually happening. So a quick reminder of what to report. Again, probably 80% of the basic class goes in depth on this, because in reality, we want you to know the science, but we really want you to report weather to us when it gets bad. So if you have tornadoes or funnel clouds, we certainly want to know about that. We mentioned in the basic class, you have got to have rotation. So don't just call in with a low-hanging triangular cloud. It's got to be rotating. If it's in contact with the ground, it's a tornado. If it's rotating, but it's not in contact with the ground, it's a funnel cloud. Any size hail, measure it with a ruler or use a reference such as a coin. Do not use marbles to reference hail. Wind speed, do you have damage? Trees down, branches down. Hopefully you have a rain gauge, a CocoRa's rain gauge. We're going to talk about that. Specific rainfall amounts are good. Any type of flooding and overall storm damage we want to know about. By far, the best way to make a report is the 800 number. This is specific to our office. So if you don't live in one of those areas we mentioned in Eastern North Carolina, this is what's going to be different. With your local office, you'll have to get the 800 number and email from them. You'll have our certificate. You can tell them, hey, I took the class out of Morehead City. I just need your contact info to make my reports. The procedure will be the same no matter where you are, who you are, what you saw, where you saw it, and when. And then again, that 800 number is just for our office. We prefer the 800 number because we can ask you questions and it's instant. We answer that phone 24/7. Other things like email, they're good, but we don't check them as frequently. We certainly check it, but it doesn't ring into the office like the phone. With the email, you can certainly give us some pictures or videos or follow up, but again, same procedure. I'm a trained SKYWARN spotter. I saw a couple trees down. I saw large hail, size of quarters. I live in Beaufort, Morehead City, Hubert, Swansboro, and where you saw it, or when you saw it. All right, so that's the quick and dirty, kind of the basic class condensed into 10 minutes. Now the next 35 minutes will be the advanced class. And I know some of you have taken a lot of the classes and you probably wonder why we repeat. Keep in mind, with our current situation, we usually do these classes spread out through the whole year. So people may have not been to a class in a couple years, or we may have new material. So all of our classes, we lay the groundwork, who we are, what we do, why we need you, and how to report. Then we go into the extra stuff. If it's tropical SKYWARN, we go into hurricanes. If it's flooding, we talk about flooding. In this class, we're going to talk about the science. So when we start with the science, we're going to talk about the basic radar. There's a couple images on here. The first I want you to pay attention to is this yellow triangle. That represents the radar itself. This green line represents the Earth that is curved. The two yellow lines represent the radar beam. And so this is the radar beam, and as it goes out farther and farther away from the radar, so as we go from left to right, when it's all the way out here, the beam of the radar is up higher in the atmosphere, and that's because the Earth is curved. Because of that, the radar does see storms and precipitation, objects that are closer to the radar better. As the beam gets farther out, since it's higher, the radar has trouble seeing things closer to the ground. So the whole point of that slide is the farther away from the radar you are, the higher into the sky you're seeing. If it's a really tall thunderstorm, doesn't matter, we can see it. But if it's something close to the ground, rotation, snow, drizzle, something that might not have a lot of depth to it, it's harder to resolve. And on the bottom, this kind of crazy picture is just showing that we have a lot of scans of the atmosphere above us. And the bottom of this graph goes from 0 to 120 nautical miles. And it's just showing that below the lowest beam of the radar, there's a little area that we have trouble seeing farther away. That's basic scientific fact. So a circulation 7,500 feet is easy to see, say 20 to 30 miles within the radar, because we've got all this coverage. But once you get beyond 100 miles, we're kind of missing some of what's going on. So that's just to re-emphasize that the radar is awesome, but there's some limitations. But that's where other things come into play. Spotters, GOES 16 satellite. We have a lot of other things we can look at than just the radar itself. The basic radar, the one that you see, is usually the reflectivity mode. That's the picture on the left. The darker yellows and reds indicate higher intensity. That's either rainfall. If it's super high intensity, it could be ice pellets like sleet, mixed precipitation like rain or snow, or hail. And then the lighter blues and greens indicate light intensity, light rain, light snow, drizzle. Where you don't see any color, that is nothing going on, no reflectivity or energy coming back to the radar. So that's what it looks like to you on the left. On the right is the diagram of how it works. The actual radar, it's really cool. It is a huge, huge satellite dish. If you have DirecTV or Dish, you kind of have a small satellite dish. This one is about 25 feet across, and it rotates around very fast, and it sends out a pulse of radiation into the atmosphere. If you've ever seen a radar from the outside, you don't see the satellite dish, you just see the soccer ball, the protection for it. But this radiation goes out into the atmosphere and it hits targets. And the radar is listening and has a transmitter that sends out this radiation. And most of the time, I think it's like 58 or 59 minutes in an hour, it's listening to what's coming back, the scattered pulse. And depending on what comes back, that can show us the intensity. So that's the reflectivity mode of the radar. We can see things like this hail core, this bright magenta shading is showing that there's high intensity, likely hail. And then whenever we see off the back of a thunderstorm, this lower intensity kind of spiking out, that's an indication of hail, and it's called a three-body scatter spike from large hail. We see these more now that we have a higher resolution radar. They used to be less common. Now they're more common and indicative of hail, and the more you see of them could be large hail. This is a cross section of the radar. So instead of just one level, we're looking up into the atmosphere. It's like an MRI of the atmosphere. Instead of your knee or your arm when you go to the doctors, it's showing a cross section in the environment. And whenever you see this white shading or pink, this is very, very high in intensity reflectivity. And you probably can barely see those numbers, but this is 21,000 feet. This is 28,000 feet. So we're way up there. We're certainly below the freezing level. So that's an indication of hail. And notice how it's tilted. If you remember from our basic class, any storm that's tilted has a better chance of being severe, has a better chance of maintaining itself. And in this case, the hail has a better chance to making it to the ground. So that's reflectivity. You're probably most familiar with that because you see it on TV, or for some of you, you might have a radar app. A mode that you might not be as familiar with is the Doppler mode, where we can see the wind, either storm relative velocity or straight velocity. And it shows up as blues and greens. On this, all of these areas that are green are particles that are moving toward the radar site itself. All the particles here that are shaded red are moving away from the radar site. So our radar on this one is down by the bottom of the screen. So this whole green area is moving toward the radar, and the whole red area is moving away. I'm going to try to get fancy. Sometimes I don't have the best luck with these pointer cursors. So we're going to try. Let me see. I'm going to try to do the pen. All right. So this green area, let me change my color because that is just about impossible to see. So we're going to do yellow. All right, that should be better. So this area here in green is all moving toward the radar. And this area in red, I hate when the pen does that. I don't know why it does that. Any tech experts out there can probably help me, is moving to the north in this case. So all we're trying to show you is red is away, green is toward. The importance of that is, try to erase these. Usually that works. So let's get rid of this. All right, erase all ink. Okay, let's get back to the laser pointer, my trusty one. This is just showing, what's moving toward and away from the radar. If we have those right next to each other and there's a thunderstorm, that's a good indication of strong rotation and likely a tornado. And you might say, well, Eric, there's green next to red here. How do you know that these are not all tornadoes? It's got to be located with a strong thunderstorm. And notice how this kind of stands out as it's separate. So that's an example of how we can see strong rotation on the radar. It has got to be with strong reflectivity, kind of in the same spot. And this is what I mean by that. Here's our area of rotation. Again, green's toward, red's away, and it's located with a very, very strong thunderstorm. And notice it's a hook shape. That's showing a rotation, we call a hook echo, and very strong updraft. So it all makes meteorological sense. Whereas up here, yeah, you got different colors, but it's a very broad area. That it doesn't make sense to have a tornado, was at 2.5 counties wide. That doesn't make any sense. It's got to be something small scale like that. So that's where we use the reflectivity and the velocity together to detect rotation. Our radar doesn't necessarily see a tornado, it sees strong rotation. And the science is, if it's in a favorable environment for it to come down, we would issue a tornado warning. So that's basic reflectivity 101, the reflectivity and the velocity part. In the early 2010s, I think it was 2012, 2013 now, it seems like the years are flying by, we did an upgrade called a Dual-Pol radar upgrade. And the way that works is the conventional radar on the left, or I love this animation on the top, it sends out radiation in a horizontal plane. So it sends it out, it bounces back, it comes back all in the horizontal. With the upgrade in Dual-Pol, we see the horizontal pulse, but we see the vertical pulse as well. So I think the image on the left does a good job. It's showing you the horizontal and the vertical. So we're getting a much more 3D picture of the particle, and it helps us to do a lot of things. One of them is hail size, droplet size, raindrop size, helps with radar estimation of rainfall. It helps with estimation of, is it a hailstone? Is it a rain or wet snow? Is it debris from a tornado? And I'll tell you about that in a second. A couple crazy terms: differential reflectivity, correlation coefficient, and specific differential phase. We're going to focus on correlation coefficient. To me, that's the one that probably makes the most sense to you from a visual perspective very, very quickly. It shows you the homogeneity of the radar echoes, and all that means is it is it all the lights same size and shape, or is it a mix of stuff? Is it all raindrops, or is it some raindrops, some sleet pellets, and wet snow? And I'll give you some examples coming up. One example are birds, insects, and anything that flies. The radar can pick that up. We see this often at sunrise and sunset. They're a different shape, so we can see flocks of birds taking off, and they're often different sizes and shapes. And that's how we can use the correlation coefficient really to show that. The reason we can use that is a high correlation coefficient on the far right is uniform. Everything's the same raindrop, snowflake. It's going to have a CC above 0.97. Don't worry, you don't have to remember the values as much as you're going to see it on this image clear as day. When we start to get down into the 0.8 to 0.9 range, that shows up as a different shade of pink and some yellows introduced. And that means that we've got some things mixing in. Debris, hailstones, wet snowflakes, sleet pellets, it's not all the same. And then when we're way below 8, that's saying things that are non-meteorological, things like birds and insects, and again, maybe debris and a tornado. And I'll show you what I mean by that. So, you don't have to remember the numbers, but this CC on the left is showing that everything is the same. So this whole pink shaded area, and we can do, if it's in the summer, we know it's all rain. If it's in the winter, it's all snow. We can use other tools like temperature observations to confirm what it is, but we know whatever that is, it's all the same in this area. It has a high CC. How about this? It's not all the same. You see the difference? On the left, it's 0.98 or higher, and it is all kind of that dark pink or purple shading. And on the right, it's way below 0.9. It's kind of craziness. So that's showing that it's not uniform. So you might say, well, how does that help? And I need to adjust this to a movie because the still doesn't do it justice. But on this, you can see there's a lot of green everywhere. And with my background, I can surmise that this is the rain. And these circles around the radar, a lot of times we refer to that as ground clutter. We'll see this in the morning or at night. The radar beam is bounced back down toward the ground, and we just pick up a lot of false echoes. But to the person that doesn't know meteorology, you might think that this is all rain. But if you turn it on to the CC mode, I'm going to toggle back and forth. Again, rain, rain, rain. I'll leave my cursor over the rain. And notice how it has a high CC. So that's an area of rain, high CC. This, again, well, could be rain. No, low CC. So you can see how the pinks pick up what is real and what is not. It's an awesome tool for the rain snow line. We use it all the time. From observations, you might see snow north of a line and rain south of a line. When you see that purple progress south and in the middle is kind of craziness, that's your mixed precipitation line. It's phenomenal for that. It is also, unfortunately, phenomenal for detecting larger tornadoes. It's not a good warning tool because it means that it's already happening. It confirms it's happening, but it means it's already happening. And here's the example. Our basic reflectivity, again, here's our hook echo, indicating rotation right there, high reflectivity right there. Here's the storm relative motion. Again, red is away, green is toward. It's really in one spot, and it's co-located with that reflectivity. And notice the reflectivity is high. That's probably some debris, but we can confirm that with the CC. This area that's all pink is rain. This area that is kind of that orange and yellow, this is mixed rain and hail. And then this really, really bright spot that it shows up with low CC, this is like 0.4 to 0.5. It's in the same spot as this, which is in the same spot as that. So again, you got to tie it all together. You can't look at CC first and say, oh, that's a debris ball. You got to look at reflectivity, check, it's high. Strong rotation, check, it's strong. and a correlation coefficient that's really low in the same spot. Unfortunately, that is the radar picking up on debris. Debris is irregularly shaped. It's not all the same size like a raindrop or a snowflake, roughly speaking. There's trees, there's parts of buildings and stuff like that. So that's how the dual-pol can help us, unfortunately, determine that a tornado is on the ground, especially if it's a big enough one to loft things up into the air. So why are we so concerned with thunderstorms? We're going to talk about that. They can produce a lot of different things: lightning, tornadoes, high winds, and hail. And we're going to go over some of those. You might remember from the prior class that thunderstorms produce, or severe one, 58-mile-per-hour winds and or large hail, 1 inch in diameter. That is our criteria. If the wind speed is less, if the hail size is less, that we don't consider it a severe thunderstorm and we wouldn't issue a warning for it. It's criteria based on when damage occurs. Keep in mind that all thunderstorms are dangerous, so I don't want to, people to think that it doesn't mean that that thunderstorms aren't dangerous because they're not severe. Any type of lightning, you can certainly have issues. Okay, so I do see a couple questions, and I want to try to make this as interactive as possible. So we're going to stop at this point. If you've got a question, ask it. I see Joseph has a question. Do we get certificates for these classes? You do. We're backed up a little bit. I still owe the last class. I think it was a flood one. I got to owe them a certificate in this class. So yes, within the next week or so, based on if you attended and you were here the whole time, because we can track who came and went, you will get a certificate. And then Ryan had a good question regarding the wind, rotation, and storms. Do computers assist in the forecast, or is it all done by a meteorologist? Very, very good. So that's a tough one. The computers certainly assist in the forecast or in the warning, but it's up to the human to actually do it. So what I mean by that is, me physically, I can't, have a radar. I need a computer to ingest that data and provide it to me on a screen. So computers help with that. Computers have certain alarms. We have settings that would alert us to strong rotation or alert us to hail size. So they can help show us the data, allow us to interrogate the data, even highly suggest we should issue a warning. Alerts will come up and we can have certain settings. But the human steps in and says, yes, based on my training, I'm going to issue a warning. Or yes, based on my training in the environment, we're going to issue a warning. Because a computer is very binary. It's either it is or it isn't. So sometimes it'll come up with an alert for, say, strong rotation, because specifically speaking, it is right, there's strong rotation, but the environment might not be supportive of a tornado, or it might not make sense meteorologically that the rotation is in that area. So I hope that answers it. And that was a fantastic question, Ryan. Very, very good. So as you can see, you can ask a question through the webinar itself. Nobody else sees those questions, so don't think that you can ask pretty much whatever you want. So we're going to go over the ingredients for thunderstorms. We mentioned this in the basic class, so I won't go over it too much, but you need instability. You need fuel for the storms, a difference in air masses. If it's really, really warm at the surface and really cold aloft, that air is going to naturally rise. Or you could have cold air coming into a warm atmosphere. So instability is the fuel for the storms. The more instability you have, the more potential you have for severe weather. And I'm kind of going through that part quickly because, again, we go more in depth on the basic class. I want to get to the advanced part. We measure this by something called CAPE. We love acronyms in weather. Convective Available Potential Energy. It's a measure of buoyancy, how likely the air is to naturally going to want to rise. If it's more buoyant, higher CAPE, it's more likely the storms are going to be severe because you have more fuel. Roughly 500 to 1,000 is enough to produce thunderstorms. Last night we had around 500, a little less, so we were kind of missing out on the instability. That's why we didn't have severe weather. 1,000 to 2,500, that J/kg is joules per kilogram. That's when you're more likely to have severe weather, and above 2,500 could be a big outbreak. Those are general terms, but roughly at least a couple hundred joules of CAPE for thunder. But again, it doesn't fit every situation. There's many days we have over 2,500 joules of CAPE in the summer. We're hot, we're humid, We're just an unstable atmosphere in the Carolinas, often in the summer because we're so hot and humid. But think back to our basic class. Just because you have all this potential doesn't mean it's going to happen. And we're going to talk about that in a second. But you need a lifting mechanism. You need moisture. And if you're missing those, you can have all the potential in the world. Doesn't mean it's going to happen. This is an older graphic, but it's from the Storm Prediction Center. We'll have that link in your email. It's spc.noaa.gov. They do a really good job. They have a mesoanalysis page you can click on. And in fact, let's just quickly, for the sake of time, hopefully I'm not going too long, but let's just pull it up real quick rather than talk about it. So this is the Storm Prediction Center, NOAA.gov. There's an enhanced risk today. These are the men and women out in Norman, Oklahoma that issue the outlooks to day 8 for potential for severe weather. And then in coordination with the local office, they will issue tornado watches, thunderstorm watches for severe weather. But at the very top, there's convective outlook, which will tell you, the general risk. But at the top is something called mesoanalysis, and you see all these boxes on the screen. If you click on your area of interest, I'm going to try to do southeast or northeast Texas and Oklahoma because I did a little forecasting today, and I know this area is primed for some severe weather. At the top, you can look at some different things, and I'll look at one of them. I'll kind of go back and forth between the presentation, but the one we are showing you, and it might not be that high yet, is CAPE. We'll look at mixed layer CAPE, and yeah, it's nothing to write home at yet. You can see some down toward the southern part of Texas. So I'll go back to my presentation, but that's how you can look at it on the SPC site. So back to the map itself. Let me get my laser pointer going. This is joules per CAPE or joules per kilogram. And again, this is 1,000, 2,000, and I know it might be hard to read, but that's a bullseye of 2,500. So on this particular day, a lot of instability is across Illinois, not as much down toward Texas or the Dakotas. So again, that's how we show it on a either a forecast map or on a predicted model. The reason why instability is important, it leads to a stronger updraft. That's that rising air. A normal thunderstorm, 30 to 50 mile per hour updrafts, and notice in a normal thunderstorm, that's about the wind speed you get in the downdraft. A severe thunderstorm, the winds are going up 50 to 70 miles per hour. What goes up must come down. That's where you get your severe gusts to 60 to 70 miles per hour. Supercells and really, microbursts, downbursts that are super strong, your air is rising in the thunderstorm at 100 miles per hour. So the downdraft can be equally as strong. So instability is fuel. The more you have, the stronger the updraft. You need moisture. It helps increase instability, and it also helps to increase updraft strength. We mentioned here in the Carolinas, we have a moisture flow off the Atlantic Ocean and the Gulf of Mexico. So we're usually not missing moisture. Moisture increases instability because water vapor is actually lighter than air. So air is made up of mostly nitrogen. 78% of our air is nitrogen, and about 21%, luckily, is oxygen, so we can breathe. But on the weight of it, notice the weight of H2O, which is water vapor, is much, much lighter. So the more water vapor you have, the more buoyant the atmosphere is because it's naturally going to want to rise since it's lighter. When that moisture condenses, it forms clouds and precipitation, but latent heat is also released. More heat, more instability, and it kind of builds on itself. So moisture and instability both can kind of help each other to create more instability in the atmosphere itself. And we use instability, we measure it with CAPE. To measure moisture, we use something called precipitable water, or P-watts. It's measured in inches. 1 to 2 is good for thunderstorms. Anything above 2 is torrential downpours. We have that a lot in the Carolinas. So this is back to that same map. A little easier to read, but anywhere above 1 on this map is a P-watt, or precipitable water above an inch, and this 1.5 is across Illinois. So remember, our best instability this day was over central Illinois. Our best moisture is over central Illinois, so they've got a couple of the ingredients right there. Another one is a lifting mechanism. We talked about this in the basic class, so I'll go over it. Cold fronts. Cold air pushes in, abruptly rises the air. That's the lifting mechanism. Cold air is dense and it forces the air to rise. You tend to get taller storms along a cold front. They tend to be much more vigorous. A warm front lifting mechanism. Warm air is coming in. The cold air is dense. It doesn't want to move, so the warm air gradually rides up above it. That's why you see this slope with warm fronts. The showers and clouds tend to be shallow and flat. Doesn't mean you can't have thunderstorms, doesn't mean they can't be severe, but compared to a cold front, the process is not as deep or vigorous. So apples to apples, they don't tend to be as strong. You can get lift over a mountain. When the air naturally goes from west to east across our state of North Carolina, it's forced to rise. That's why they have a lot of puffy clouds along the Appalachians over toward Asheville and Boone in the summertime, because that air is forced to rise over it. Thunderstorm outflows. So we mentioned in the basic class, you have an updraft in a thunderstorm, and then you have a downdraft, the exhaust part. That exhaust is rain-cooled air, and as it hits the ground, it spreads out. It's like a mini cold front. So on this diagram, as a downdraft hits the ground, it spreads out in this arcing pattern. And you can see this on radar. I keep making these mental notes, but I've got to add some radar imagery. These skinny little lines, these outflow boundaries, you can easily see them on radar, and they'll tell us where those outflows are. The other thing I got to add is the sea breeze. Again, mini cold fronts, because of the difference in heating. Land heats up faster, water heats up slower. Difference in pressure from high to low pressure. High pressure over the water, low pressure over the land causes the air to naturally flow in off the ocean in the summertime. That is another type of boundary or lifting mechanism. So instability is measured by CAPE. Moisture is measured by precipitable water. Lifting mechanism, that would be some type of front or low pressure system or boundary. And the last one is wind shear. We briefly touched on this in the basic class, but there's two types, directional and speed. Directional just means that the speed changes direction with height. So on this example, this is a southeast wind, south-southeast wind, southwest wind, west-southwest wind. And the blue line or pole indicates I'm going up in the atmosphere. So that is a veering with height. We're going from southeast to southwest in the lower part of the atmosphere. Direction changes with direction. Speed shear is these line segments represent wind speeds. The longer the segment, the stronger the wind. The shorter the segment, the lighter the wind. So this is just showing as we go up in the atmosphere, the winds are getting stronger, and that's represented by that longer line segment. And that can induce shear, or I call it a twist in the environment. But either type of shear involves a twist or a rotation. And if that rotation gets over a strong updraft, it gets stretched, and that's how a tornado forms in real simple terms. Shear also in the atmosphere can have a thunderstorm that rotates. A naturally severe thunderstorm actually rotates. It's not the rotation you see of a tornado, like small scale. It's just a slow moving, and that's the rotation of a thunderstorm itself. So instability will determine how strong the storm is. High instability, high potential for it to be bad, and the shear determines what type it is. If you have shear, if you don't have a lot of shear, and again, we're going back to the wind graph, south wind, south-southwest, southwest, not a lot of change. It's unorganized. You're going to have pulse storms. Remember from our basic class, the storm is going to develop and then it collapses on itself because it doesn't have enough shear. With supercells, you go from a southeast wind to a southwest wind really, really quickly. A lot of rotation, a lot of shear. It's going to allow the storm to maintain itself and potentially produce large hail, gusty winds, and even tornadoes. So this is how we measure shear. This is back to the mesoanalysis page. For you that it's hard to read, this is 50 knots of shear, 60, and the bullseye is over Oklahoma, 70 knots of shear. Generally, we want 35 knots of 0 to 6 kilometer shear. That's a good lower section of the atmosphere. Anything above 35 to 50, the weather gets more serious in terms of potential. And again, you can't look at just one. You can't say, wow, the shear is crazy, we're going to have tornadoes. It's not that simple. You need instability, a lifting mechanism, then it all has to come together. So there's many, many times where the ingredients are in place and one is just not adequate enough, luckily, for weather to be bad. Couple more slides and then we're going to turn it over to you for questions. We're at about the 40-minute mark. This is aiming for about a 45 to 50-minute class. It is more in depth than the basic. So we mentioned if you have weak shear and instability, you get the single cell or pulse storm. What that means is, again, the storm pulses up and it collapses. So the life cycle of a thunderstorm, the updraft begins. The mature stage, you have a really strong updraft and a really strong downdraft. This is the intake, the warm, moist air. And then the front side of the storm, the downdraft, the exhaust, that's where our air is rain-cooled, heavy rain, gusty winds, shelf clouds, hail, that type of thing. And then the last stage, the storm falls apart and it dissipates in the dissipating stage. The reason why we mentioned that, going back to the single cell, the difference between a single cell and a supercell, a single cell goes from here to here to here, 20 minutes for just that one individual storm. You may see a lot of them on the radar, but they pulse up, they get red, and then they collapse. A supercell goes from here to here, and it may last an hour. Or multiple lines of cells may last hours, and then they eventually collapse. So that's the difference. More shear and instability leads to more longevity. I mentioned that you have strong updrafts in a thunderstorm, but you also have strong downdrafts. When those hit the ground, we call those microbursts. You have wind speeds over 100 miles per hour, and they can produce damage like this. Notice a lot of trees down. Sometimes people think it's tornadic if there's a lot of damage, but if the damage is pointed in the same direction or a divergent pattern, which means these trees are pointed this way, these trees are pointed that way. This is, if you see the black arrows, divergent is a fan-shaped. That is indicative of a microburst. It's like you dump a cup of water and it spreads out in one direction or it gradually fans out. A divergent pattern is a microburst. And again, from that damage, we're talking hundreds of trees are down. So it's not that you can't have 100-mile-per-hour winds. It's the pattern that determines if it's a tornado. So as we increase updraft strength and instability, we can get multiple cells. Again, longevity. More shear allows the storm to organize into a line. Here's a squall line. Again, a lot of times these can form ahead of a cold front, a strong lifting mechanism. A lot of times on a squall line, we'll look for bow echoes. Anytime you see this bow shape, it's an indication there's very, very strong winds pushing that out. Things don't just happen in Mother Nature because it's bowing out because there's strong winds. This is a nice diagram of that. Here's your line of storms. If there's no strong line, if there was no strong wind associated with it, it would just kind of progress along. But if there's really, really strong wind, this is yellow arrow is indicating a low-level jet, and that's pushing that line out. So now you can see how it bows, and then the top and bottom kind of curly Q around. So that's just showing the evolution on a model sense of a line transitioning into a bow echo. And the worst shear and the worst updraft strength would be a supercell. Here's our classic picture of a mature supercell. It looks very similar to the mature stage of a thunderstorm. A supercell is just a textbook classic severe thunderstorm. You have very, very strong, this is a reciprocal of the other image, but same concept. Very, very strong warm, moist air going into the storm. This is the updraft. Very, very strong lift here, and this is where you would actually have the most likely place for a tornado, is the backside of a classic supercell. That would be the hook echo region. The front side of the storm, the air is descending, rain-cooled air, shelf clouds, strong winds, and hail. And again, that's a textbook definition. This is what it looks like on radar. Again, this is the hook echo, the back side of the storm, the rotation, and then the front side of the storm is this heavy rain, wind, and maybe some hail with it. So that's what it looks like on radar. We rate tornadoes based on a damage scale. We don't know the actual wind speed. We just look at the damage, and depending on the damage, we have a chart, a binder, and we have a range, lower bound, average or expected, and upper bound. And we have damage indicators for everything: mobile home, two-story home, apartment, brick building, softwood tree, billboard, anything you need. And it'll show us, if you have certain damage indicators, how strong the winds are. So we look on a survey for how strong the winds were, and then it's pattern for tornado or microburst. It has nothing to do with the amount of damage. You can have a tremendous amount of damage and have a microburst. But contrast this picture to the one we showed you earlier. These white arrows are pointing in this direction, and then these white arrows are pointing in this direction. That's a convergent path. And you can even see these trees out here are angled this way, and these trees here are angled in. A convergent pattern is a tornado. It's hard on our weaker ones to determine that. That was an EF3, the one you just saw, so it's pretty clear. So we're going to wrap things up. When to report to us, again, tornadoes or funnel clouds, any size hail, flooding, and 2 inches or more of rain. We prefer the 800 number. Again, if you're not local, you need to hook up with your local office, and I can facilitate that. Email is good for follow-up pictures and video, and we get reports on social media as well. So we're right at the 45-minute mark. I hope for those that attended the basic class, this was a nice follow-up. I will admit that our virtual training is always shorter. In-person classes are an hour and a half, hour and 15 minutes. We can take a break. I can talk. I can see if you're, if one part is too confusing or too much, and I can move on. The virtual class, I can't see you. So we try to keep them to 40 to 45 minutes so that we're not losing anybody. So at this point, you're done. If you want to log off, you can. In the next week or so, I'll send you a certificate. If you don't get one weeks from now, email me. That means that the email address is wrong, or something got messed up with your registration. So my email is right there, and it's all over our website, so it's pretty easy to find. At this point, it's all yours. We'll take about up to 5 minutes of questions. So if you have one, ask them through the webinar feature. I'm going to start looking at that. And raise your hand if you want to ask an audio question. But at this point, you're free to log off. You're also free to stay on for any questions.